There is a moment in the history of human civilization where the modern world, the one of radios, televisions, computers, and smartphones, balances on the edge of a single glass bulb, no bigger than a man's fist. Inside that bulb, in a vacuum so complete it borders on the philosophical, electrons obey a command. They flow in one direction only. And with that, the 20th century begins. The man who made it happen was not a glamorous figure. He was not a showman like Edison, nor a tragic genius like Tesla. He was a meticulous, precise, deeply Christian English engineer named John Ambrose Fleming, and the story of his greatest invention is wrapped in theft, legal fury, wounded pride, and a battle for credit that consumed the final decades of his very long life. John Ambrose Fleming was born on the 29th of November, 1849, in Lancaster, England. His father was a Congregationalist minister, and the household was one of discipline, faith, and intellectual rigor. From an early age, Fleming showed a fascination with how things worked. By the time he was 11, he had built his own small workshop and was constructing working model engines. This was not a child who needed encouragement to think. He needed walls to keep him from thinking too far ahead of his teachers. He studied at University College London and later at Cambridge under the legendary James Clerk Maxwell, the man who had mathematically unified electricity and magnetism into a single theoretical framework. Sitting in Maxwell's lectures was like drinking from a fire hose. The physics was dense, radical, and world-altering. Fleming absorbed it all. Maxwell would die in 1879, leaving behind equations that Fleming would spend a career trying to apply in practical form. Fleming's professional life wove between academia and industry in a way that was unusual for his era. He became a scientific advisor to the Marconi Company, working alongside Guglielmo Marconi himself at the turn of the century. It was in this role, straddling the theoretical and the commercial, that Fleming would encounter the problem that led him to his greatest invention. Here is where the story takes its first dramatic turn, and where the ghosts of other men begin to haunt Fleming's legacy. In the early 1880s, Thomas Edison, experimenting with his incandescent light bulb, noticed something strange when he inserted an extra electrode into one of his bulbs and applied a voltage. Electric current would flow through the vacuum from the hot filament to the cold plate, but only in one direction. It would not flow in reverse. Edison noted it, filed a patent in 1884, and then did something extraordinary in its indifference. He set it aside. He had no idea what it meant. It did not help him sell light bulbs. So it sat. This phenomenon became known as the Edison effect, and for nearly 2 decades it remained a scientific curiosity, an unexplained anomaly that physicists discussed but no one weaponized. It was Fleming who finally looked at that forgotten mystery and saw a tool. By the early 1900s, Marconi's wireless telegraphy was creating enormous excitement. The ability to send messages through the air without wires seemed almost supernatural to the public, and commercially, it was a gold rush. But the technology had a crippling weakness. The detection of wireless signals, the receiving end of the communication, was unreliable, inconsistent, and frankly primitive. Engineers were using devices called coherers, which were tubes filled with metal filings that would clump together when radio waves hit them. They worked after a fashion, but they were clumsy, insensitive, and had to be physically tapped back to their original state after each signal. It was like trying to build a telegraph network using wet clay. Fleming knew there had to be a better way. He needed a device that could take the oscillating, alternating current of a radio signal, which swings positive and negative many thousands of times per second, and convert it into a smooth, readable, direct current. In electrical terms, he needed a rectifier. And then, in 1904, he remembered Edison's old bulb sitting in the drawer. Fleming's insight was breathtaking in its elegance. The Edison effect, that strange one-way current through a vacuum, was exactly the property he needed. If electrons would only travel from hot filament to cold plate, then alternating current fed through such a device would emerge as direct current. The negative half of each oscillation would simply be blocked. The signal would be rectified, detectable, readable. He constructed his device in the autumn of 1904. It was a sealed glass bulb, evacuated of air, containing a heated filament called the cathode, and a metal plate called the anode. When the filament was heated, it shed electrons into the vacuum. Apply a positive voltage to the plate, and those electrons streamed across. Apply a negative voltage, and they did not. Simple, elegant, revolutionary. Fleming called it the oscillation valve, though it would become known to history as the thermionic valve, or in America, the vacuum tube. He filed his patent in November 1904. The patent number was 24,850. It was, in every meaningful sense, the birth certificate of modern electronics. He wrote to Marconi with barely contained excitement, describing the device as a new and original instrument. He was right, though he could not yet fully grasp just how original. In practical terms, it meant that wireless telegraphy could now detect signals with vastly greater sensitivity and reliability. In theoretical terms, it meant something even larger, that human beings now had the ability to control the flow of electrons deliberately, precisely, and in ways that could be made arbitrarily complex. The age of electronics had begun. If Fleming's story ended with the invention of the diode valve, it would be a clean and satisfying narrative. It has not. In 1906, 2 years after Fleming's patent, an American inventor named Lee de Forest added a third element to the valve, a grid of wire placed between the cathode and the anode. This new component, which de Forest called the Odeon, meant that a tiny voltage applied to the grid could control a much larger current flowing through the device. The valve was no longer just a rectifier. It was an amplifier. De Forest's triode, as it was properly named, was world-changing. It made long-distance radio communication possible. It made radio broadcasting possible. It made, eventually, the entire electronic revolution of the 20th century possible. And Fleming hated everything about it. The conflict between Fleming and de Forest was not merely professional jealousy, though there was plenty of that. It was existential. Fleming believed, and argued with increasing fury for the rest of his life, that de Forest did not fully understand the physics of his own device, that the Odeon was a direct theft of his foundational concept, and that the credit for the electronic age rightly belonged to him. The legal battles were ferocious. Fleming's employers and de Forest's backers fought through the courts for years, in disputes so tangled and expensive that they became famous in patent law circles as cautionary tales about what happens when transformative technology arrives, and multiple parties reach for the credit simultaneously. In 1943, the United States Supreme Court, in a case involving de Forest and others, voided several of de Forest's key patents, finding that the science had not been properly understood. Fleming took considerable satisfaction in this, though by then he was 93 years old, and the fight had lasted longer than most careers. What the conflict really exposed was a painful and recurring truth about invention, that the first step and the decisive step are rarely taken by the same person, and that history, commerce, and ego do not distribute credit fairly. Fleming's life was not lived entirely inside laboratories and courtrooms. He was a deeply public figure, and not always for reasons he would have chosen. He was an outspoken Christian, and late in his life he became a prominent anti-Darwinist, campaigning against the teaching of evolution and helping to found the evolution protest movement in 1932. This put him in direct conflict with the scientific establishment he had spent a lifetime serving, and earned him considerable ridicule from colleagues who felt a man of his achievements deserved a more dignified twilight. He was knighted in 1929, becoming Sir John Ambrose Fleming, but the honour sat awkwardly against his increasingly eccentric public positions. He was also profoundly deaf for much of his adult life, a condition that he managed with determination and that perhaps deepened his tendency toward isolation and intense written correspondence rather than collaborative work. His first wife died in 1917 after a long illness, and he remarried in 1933 at the age of 83 to a woman named Olive Franks, who was 50 years his junior. The marriage raised eyebrows in polite society, but by all accounts it was a genuinely happy one. He lived to 95 years old, dying on the 18th of April, 1945, just weeks before the end of the Second World War, a conflict fought substantially with technologies his invention had made possible. It is worth pausing to understand what the thermionic valve actually unleashed, because the numbers are staggering. By the 1940s, vacuum tubes were being manufactured at a rate of hundreds of millions per year. The first electronic computer, ENIAC, completed in 1945, contained approximately 18,000 vacuum tubes and occupied a space the size of a large room. Every radio receiver, every television set, every piece of audio equipment in the first half of the 20th century was built on the foundation Fleming had laid in his workshop in 1904. Then the transistor arrived in 1947, which was itself a solid-state evolution of the principles Fleming had demonstrated. And then the integrated circuit. And then the microchip. Every device you have ever used that processes information electronically traces its ancestry, in a direct and unbroken line, to that glass bulb with the hot filament and the metal plate. The global electronics industry today is measured in trillions. The device Fleming built would fit in your palm. History has a tendency to worship the glamorous and forget the foundational. Edison and Marconi and Tesla have statues and museums and popular biographies. Fleming is known primarily to engineers and historians of technology, which is a strange fate for the man who arguably did more than any single individual to make the electronic world possible. The conflict with DeForest, the anti-evolution campaigns, the eccentric late marriage. These things have colored his legacy in ways that obscure the central fact. In 1904, John Ambrose Fleming looked at a forgotten curiosity from Edison's notebook, understood it deeply, and turned it into a working device that changed the trajectory of human civilization. He was difficult. He was combative. He held views that aged poorly. He spent decades fighting for credit he felt was owed to him, with a tenacity that sometimes crossed into bitterness. But he was also right. The thermionic valve was his. The electronic age carries his fingerprints. And every time a signal travels through any device on Earth, every phone call, every internet packet, every stream of music through a speaker, it does so because one meticulous Englishman looked into a glass bulb and saw the future.